Alright, welcome back. This will be a short tutorial on the D latch and D latch with enable. So this is another set reset latch. In this case, we're going to be using a single input D for data with an inverter. So here in the simplified D latch, we see our D going into R prime, and we're inverting that input going into S prime. And this has a convenience in that we only need one input, and the inverter ensures that our input to R prime and S prime are always complements of each other. And this keeps us from, helps keep us from getting into that race condition where Q is set and Q prime is set, or they're both D asserted. They're either both asserted or both D asserted. We're trying to avoid that condition. So we see with the D latch we just have two states. It's either if D is set, then Q should be asserted, and we would say that the D latch is set. So if D is asserted, Q would be asserted. If D is deasserted, Q prime should be deasserted. We see here with the gated D latch, we just implement an enable going with the second set of inverters, or NAND gates, sorry. And then our inverter on our data is then going into the R, and the uninverted going into the S for set and reset. And then we'll just go through them. We see here with the simplified D latch, we just have the two states. If D is deasserted, then we end up with our Q being deasserted and Q prime asserted. So we'd say this is in a reset state. If our D is asserted, then our Q is asserted and our Q prime is deasserted. So we'd say we're in a set state. And we see that it's still the bistable latch. When we get to the D latch with the enable, in this case, as long as the enable is deasserted, it doesn't really matter what we do with the data input. If we deassert it, we still have a positive or an active NAND gate for set and an active gate for reset, which with the stable state keeps the two inputs, the S prime being asserted and the Q prime next being asserted, keeps the top gate inactive and keeps the Q in a reset state, and then the R prime being asserted with the Q prime next being deasserted keeps the lower gate in an active state, keeping the reset state active. So we see that stays stable because even with the D asserted, the top gate also stays active in the same state. So we stay in a stable state as long as the enable is deasserted. All right, if we go through, in this case, if we start with the latch in a reset state and we want to set it, we assert the data input, giving us an active or a high to the top gate, but with the enable still deasserted, that gate still stays active. And with the inverted data and the enable both deasserted, the lower gate still stays active. Well, remember, it takes a positive and a positive to create a negative. So now when we enable, we assert the enable, now we have that positive and positive, or 1 and 1, going into the upper NAND gate, and that inactivates that NAND gate. And we start to get a 0 now coming in on the S prime. Coming down here, we see that 0 and 1 now activate that top NAND gate, and that then starts to produce a 1, and we get the Q now in an is now asserted, and Q next is asserted. With the Q next coming in asserted and the R prime asserted, the lower gate then becomes inactive, and our Q prime is then deasserted, and Q prime next is deasserted. And of course the 0 and the 0 here keep this keep this gate active, so it continues to output a 1. All right, and so then the latch itself is back to a stable state. We can then deassert the enable, and we can see with that deasserted that we're back to an active state. If we were to deassert the data input now, we would have a 0 and a 0, which would still be a active NAND gate here, and then this would invert, and that would become a 1, and the 1 and the 0 here would still produce an active NAND gate here. So we would still stay in that stable state even if we deassert the data at this point. All right, so that was just a quick going from a reset to a set state. So our D latch and our D latch with enable, these are our gated D latch, are still bistable, still reducing. In this case, reduces the number of inputs through the use of an inverter, so that we're making sure that our S prime and R prime are always have complemented values. All right, so to demonstrate with this circuit over here, we can kind of see we've introduced a new integrated component chip. So we've had the 7.4 LS00, which is our quad 2-input NAND gates. We're now introducing a 7.4 LS04, which is a hex or 6 1-input inverters. We can kind of see where things are laid out. Each of these integrated circuits requires connection to the power rail on the VCC pins and ground rail on their ground pins. All right, so showing what the internal gate logic connection to the pins, we can see our 7.4 LS00, our quad NAND gates, are still set up the same way we had for the SR latch with enable. We're using S prime is going into this NAND gate up here. We see, and then R prime represents this lower NAND gate here, and then our S is going into this NAND gate up here and then down here. And if we look at this, once again, our Q is being represented by this yellow LED and our Q prime by this red LED. So if we look at Q and trace it back through this resistor, here's the output from that upper NAND gate for S prime, and we see that output crosses back over to be this input into the R prime NAND gate. And then the other input up here at the top is coming from the output of the S NAND gate in front of it. And then likewise down here, it got one input from the NAND gate up here, and then it gets its other input from the R NAND gate. Of course, its output leads to the red LED, which is the Q prime, and also leads back here to be an input into the S prime NAND gate. So that's our latch. And then if we trace this, the inputs for S and R, we see that for S, we have one input is coming from the enable. This green is coming back and connected to this green here and this green, and this is our enable switch. And we see it coming into this input of the lower NAND gate and into this input of the upper NAND gate. So that's the enable. This input here for the upper NAND gate is going through this yellow wire into this inverter. And well, actually, I'm sorry, this input here is coming through this white wire to the data input. So the data input is going directly into the from the white wire here into the yellow wire into this input. And that represents data going into the S. The other input being the green wire up here going to the enable switch. So we have enable and data going directly into the upper gate. When we look at the lower NAND gate, we see that one of its inputs here is coming into the enable switch. Its other input is coming from this inverter. So our data is being fed both to the upper NAND gate input and through this inverter, it's being fed down here to this lower input. So we're inverting D going into the input of the lower NAND gate as we see on this diagram. All right, so looking over here at the circuit, we have that set up. We have the 74LS00 or the quad NAND gates that we've been using for the latch. And we have the outputs coming in here to the yellow for set and the red for reset. And we have the outputs crossing back over to inputs of the perspective gates. And then we have the green wires here are representing the enable. So they're representing this enable switch, and they're being fed directly into the inputs of the other two gates. And then we see the white here is coming into the other input of this upper gate. So this is the source pin. We're using this as the enable, and then that purple wire up here is the other input for the S gate, and that's going directly to the white wire, which is going to this blue wire, which is which is acting as our data input. And the orange wire here is acting as our enable switch. So our enable and our data. Now our data is also, from this white wire, is also being fed into this top inverter. And as it comes out the opposite in the complement, it comes down through this purple wire to the other input of the lower NAND gate, the R or reset input. All right, so let's fire this up and see how it works. All right, so it's coming up in a reset state, which, remember, that has to do with the internal delays of the NAND gates in here. They have built-in delays to kind of help make sure if we're using this for a latch that we don't end up with two NAND gates outputting the same value. So we just end up in a reset state here. And so we notice if the blue is our data, it doesn't matter what value we're putting on D. So by grounding or ungrounding it, I'm changing it from a high when it's ungrounded to a low when it's grounded. So it didn't change the state of the latch. Now if I enable, or I assert our enable by pulling it out of the ground, now if I change from a low state to a high state, we go to a set state on the latch. If I go back and deassert the data, we go back to a reset state. Now if I go back here to a set state, that took a little bit of a delay, and then I deassert the enable, now it won't matter what I do. Here I'm going to deassert the data and we stay in a set state. So it doesn't matter what I do as long as we have the enable deasserted. So if I assert the enable, notice the data was deasserted, so the latch reset changed to a reset state. Right? If I assert the enable or assert data by ungrounding it, we change to a set state. So I can keep changing the state as long as it's enabled. And then if I deassert the enable by grounding it, now it'll stay in a steady state. All right, so that was a quick demonstration of our D latch.